You know that feeling when you're searching for a specific document and the search engine just stubbornly spits back results based on the exact rigid keywords you typed? It completely misses what you actually meant. It's a classic, honestly, super annoying problem. Well, today in this explainer, we're going to uncover how modern AI is finally starting to actually understand meaning. We're diving deep to demystify the core mechanics of RAG, that's Retrieval-Augmented Generation, and we're zeroing in on the incredible systems making it all work. Embeddings, embedding models, and vector databases. Let's get right into it. Okay, let's dive into this. Here is our roadmap for today's explainer. First, the magic of embeddings. Second, choosing your embedding model. Third, entering the vector database. And finally, tying it all together as the backbone of RAG. Starting off with Section 1, the magic of embeddings and how we are moving beyond simple keywords.
This right here is the foundational layer of everything we're discussing today. So, we've got to start with this fundamental question. What exactly are embeddings? I know it sounds like a highly complex mathematical term, but it's actually the secret sauce. It's the very thing that makes AI seem so intelligent and capable of understanding human language. Think about it for a second. How do you actually teach a computer what a word means?
Well, here's our definition. Embeddings are numerical vector representations of text that capture the semantic meaning and relationships of data in a high-dimensional space. Now, I want you to really notice that phrase right at the end there, high-dimensional space. We aren't just assigning one random number to a word. No way. The AI is literally mapping the relationships between concepts across hundreds, even thousands of dimensions to truly capture its semantic meaning. It's quite literally a mathematical map of meaning. How cool is that? Let's move on and see how this builds, right? How does this actually play out in a semantic search process? Well, in a RAG system, there are 3 absolutely vital steps happening. Step 1, we take the user's query and we convert it into a vector. Step 2, we've also converted all of our source document chunks into vectors. And then step 3, the system simply compares these vectors for similarity. By comparing these numbers out in that high-dimensional space, the RAG system retrieves the absolute most relevant, contextually appropriate document chunks from our knowledge base. Now, you might be wondering, why does this matter? Why go through all this complex mathematical mapping? Well, because meaning-driven retrieval is vastly superior to simple keyword matching. It's not even close. Those retrieved document chunks act as the critical context we need to generate accurate and grounded responses. This process completely transcends just, looking for matching words on a page. The embeddings form the backbone that allows the AI to understand the deep semantic intent behind your query. All right, moving to Section 2, choosing your embedding model and some tactical considerations for the real world. So we've established the what, but, an embedding doesn't just magically appear out of thin air. When you're choosing the model that creates them, there are 4 key tactical considerations that will absolutely dictate the effectiveness and scalability of your entire system. First up is domain relevance. Does the model actually capture the specific semantics of your industry? Second, dimensionality versus costs, which we'll break down in just a second. Third, dataset performance. How well does it retrieve quality results for your specific data? And fourth, the logistics. You literally have to look at the model's size, its API availability, latency, cost implications, and licensing to make sure it tightly aligns with your infrastructure constraints. Actually, let's drill down on that third point for a second, looking at academic datasets versus real-world data. You have to ensure good retrieval quality on your specific data set. Because, let's face it, real-world data is messy. It's all over the place. It often differs wildly from the clean, pristine academic data sets these models are initially tested on. A model might look absolutely perfect on paper, but then it can completely fail when it hits the reality of your company's actual, everyday documents. So the crucial point is, it really comes down to this massive trade-off. Dimensionality balances retrieval precision against computational and storage costs. This is the big decision that every tech manager and developer has to meticulously weigh. Sure, higher dimensionality might give you incredibly precise semantic meaning, but it's going to cost you significantly more to compute and store those massive vectors. You have to find the exact sweet spot for your specific system. Which brings us to Section 3. Enter the vector database. This is where the magic lives. Okay, so once our chosen model has created massive amounts of these high-dimensional vectors, we hit a scaling wall. We've got all these numerical representations, but we need a highly specialized place to actually put them. Enter the vector DB. A vector database is a specialized database designed to store and efficiently retrieve high-dimensional vector embeddings. Just like we defined embeddings earlier, this database is the dedicated engine that makes semantic search possible at blazing speeds. So how does it do this in practice? Well, the vector DB matches the vector representation of a user query with the closest stored vectors in the database. Because these embeddings are stored spatially based on their meaning, the database can efficiently perform semantic searches to find the closest neighbors. It's retrieving the most contextually relevant document chunks at massive scale, which enables the fast similarity search that's absolutely crucial for RAG systems to function smoothly out in the wild. And finally, Section 4, the backbone of RAG, tying the whole journey together. We've gone from the macro concepts all the way down to the micro mechanics, so let's bring it all to a resolution. Embeddings plus the model plus the vector DB equals scalable RAG. And this brilliantly illustrates how these three core components act as the ultimate backbone. Think about it. The embeddings capture the meaning, the model generates those embeddings based on your real-world constraints, and the vector DB stores and retrieves them at lightning speed. Together, they allow a retrieval system to pull perfectly accurate, context-rich data to ground your generative AI responses. But before we wrap up this explainer, I want to leave you with one final provocative thought. We know that embeddings beautifully capture the semantic meaning of our data at a specific moment in time. But what happens when that meaning naturally evolves? Language changes, company knowledge shifts, and contexts update. How will these RAG systems efficiently adapt when the very mathematical map of meaning needs to be completely redrawn? It's a fascinating challenge. Keep exploring, keep learning, and think deeply about that as you build and interact with the AI solutions of tomorrow.